Hey, welcome back, everybody. So this is the second talk of today, and we are very happy to have Joschka Roffe giving us a tutorial on how to decode quantum LDPC codes.
Okay, thanks for the intro. So this talk will be a high-level introduction to decoding quantum LDPC codes. Okay, so I guess why do we want to use quantum LDPC codes? And the main motivation is that we could potentially do quantum computation much more efficiently than is possible with the surface code. So with the surface code, it's been estimated that we might need about 1,000 physical qubits per logical qubit, whereas with quantum LDPC codes, this could be reduced considerably, perhaps to something like 50 qubits per logical qubit. The disadvantage, of course, is that we go from a nice structured layout of the surface code to something that looks like this pile of spaghetti. So we need something that can perform long-range interactions. Okay, and fortunately, there are various quantum computing devices being developed around the world that will enable this. So examples include silicon spin qubits, neutral atoms, as we're seeing from the recent QERA experiments. Ion traps, in principle, have the ability to perform arbitrary qubit-qubit interactions within the traps themselves. And I didn't used to include superconducting qubits on this list, but recent experiments or recent proposals from IBM and other groups have shown that it would be in principle possible to perform beyond nearest neighbor interactions using 3D integration and similar techniques. Okay, so what is a quantum LDPC code? So this was nicely explained in the previous slide, but a bit of redundancy never does any harm. So a quantum LDPC code is an error correction code where each qubit is connected to a bounded number of stabilizers. So if we take this definition at face value, then technically speaking, the surface code is also a quantum low density parity check code, because each qubit in the surface code is only connected to at most 4 stabilizers. However, what we usually mean in practice when we refer to a quantum LDPC code is one of these codes where we construct the code using a product construction or otherwise, where there's usually some sort of randomness in the construction. And this gives rise to the quantum low-density parity check codes that have the good encoding densities and nice distance scaling properties as you increase the size of the code. Okay, so just to give a quick overview of the talk. So I'll start off with some background. So go over the classical code, classical binary code formalism, the tanagraph way of representing this, and then explain how we can represent our quantum codes in terms of pairs of classical codes via the CSS stabilizer framework. Following this, we'll have all the background we need to understand the quantum decoding problem, and then I'll go on to explain how this can be tackled with a modified form of the classical belief propagation decoder called belief propagation plus ordered statistics decoding. Following this, I'll talk briefly about circuit level noise before going on to discuss the open problem in the field, which is how we go beyond this belief propagation plus ordered statistics decoder and build a truly efficient decoder that could, in principle, be used on a real device. Okay, so just to recap this again. A binary linear code, a classical binary linear code, is a redundant mapping from a k-bit data string to an n-bit code word. So here we have an example for the 3-bit repetition code. This maps a single bit to 3 bits, so 0 to 0, 0, 0, and 1 to 1, 1, 1. And any binary linear code can be represented in terms of a parity check matrix, which is defined such that all the code words are in its null space. So if the code word is uncorrupted, so it's just 0, 0, 0, and when we multiply it by the parity check matrix, we just map to the 0 vector, so we know that nothing's wrong. However, if our code word is corrupted, then it no longer maps to the 0 code word, and we get a so-called non-trivial syndrome that tells us that something's gone wrong with our encoding, and we have to do something about it. And a nice way of representing binary linear codes of this type is with a tanagraph, which we saw explained in the previous talk. I like to draw them like this, where the round nodes represent the bits, which map to the columns of the parity check matrix, and the square nodes represent the parity checks, which are the rows of the this matrix. And the rule is that each parity check, when you sum over the bits that it's connected to, that sum should be equal to 0. Okay, so if we set the bit nodes to be 111, so the second code word, then we see that this parity check, for example, is satisfied because 1 plus 1 mod 2 is 0. However, if we then flip a qubit, a bit in this case, then this check is no longer satisfied and we get a non-zero syndrome. Okay, so that's classical error correction. Now on to quantum error correction. So as with many things with quantum computing, things get more complicated and annoying. For quantum error correction, the specific problem we're faced with is the fact that we have an additional error type. So in a very simplistic way of looking at things, in classical error correction, we only really never need to worry about bit flip errors. In quantum error correction, we have an additional error type to worry about, which is a phase flip. So we can think of this as being a flip around the axis of the block sphere that's perpendicular to the one that gives you bit flips. Okay, so any quantum error correction code has to have the ability to detect and correct both of these error types. Okay, and the way that we can do this is with a so-called stabilizer code. Here the idea is that we create an entangled logical state, and then we measure sequences of Pauli operators on the state that we can think of, that we call stabilizers, and we can think of these as the quantum analog of a parity check measurement. So these stabilizer measurements are measured out via non-destructive projective measurement via an auxiliary qubit. These are measured out to give us a syndrome. This syndrome is passed to a decoder, which is just an algorithm run on a classical computer. This tells us what the best recovery operation is given the measured syndrome. And then we can then apply that recovery operation and hopefully restore our quantum information to its uncorrupted state. So this is the full decoding cycle. And the important thing is that we do this full operation, so stabilizer measurement, decoding, and recovery within a time frame that's shorter than the time it takes for the qubits to decode. Okay, and we're going to focus on a specific type of stabilizer code called the CSS stabilizer codes. And these are a type of stabilizer code where you can separate out the detection of bit flips and phase flips into two separate stabilizer extraction processes. You then get a separate stabilizer syndrome readout for bit flip errors and another bit syndrome readout for phase flip errors. They can then be decoded separately to give you two recovery operations. Okay, and the reason why we like to focus on this particular subclass of stabilizer codes, this CSS subclass, is that it provides a nice way of representing your quantum code as a pair of classical codes. So you can think of one of these CSS codes as being described or being a combination of two classical codes described by two parity check matrices. So one parity check matrix that detects phase flip errors and another that detects bit flip errors. Okay, so a famous example of one of these codes is the Steen 713 code. This encodes one logical qubit in 7, and it's defined so that both this HX and HZ components are the classical Hamming codes. And just like with the classical tannograph, we can create a quantum tannograph. So we have our 7 qubits here. We add 3 stabilizers to detect phase flips, and then we can also add an additional 3 stabilizers to detect bit flips. Okay, so this provides a nice way of viewing the construction of quantum codes in terms of the classical coding framework. Unfortunately, it isn't possible just to select your 2 favorite codes as the HX and HZ matrix, because these HX and HZ matrices actually correspond to physical operations that we measure on our quantum states. So when we are measuring the observables on a quantum state, we have to make sure that they commute. And we can make sure that this property is satisfied in terms of this CSS formalism simply by checking that this property is satisfied, i.e. when we multiply the HX matrix by the transpose of the HZ matrix, we map to the 0 vector. So this is a challenge in designing quantum codes because finding pairs of codes that give us this property is not always easy. So this is where the product constructions come in, and we can think of these as being a recipe for turning classical codes into quantum codes. So here's an explicit example. So here are two classical codes, and I've represented the parity check matrix using this image, where each black pixel is a 1 in the parity check matrix, and the blue background just represents all the locations where there's a 0. So we can see that both of these parity check matrices, well, they're actually two copies of the same parity check matrix, but we can see it's sparse because in the vast majority of the pixels are blue. Okay, and we can put it through a product construction to turn it into a CSS code, and this gives us two HX and HZ matrices that look like this. So we go from, this gives us a 416, 18, 20 code. And there are two things I want you to note about this. First of all, the HX and the HZ matrix are somewhat bigger. In this case, we've increased the number of bits necessary by a factor of about 8. The second thing to notice is that the HX and HZ matrices are still sparse. So they're still LDPC codes, and then can, in principle, be decoded using any existing classical technique. Okay. So in the first instance, it's always useful to study the decoding problem in the simplest possible error model. We call this the code capacity error model. And we, in the code capacity error model, we just assume that errors occur just before we measure the stabilizers. Okay, and because we're measuring the X and the Z stabilizers separately, we have two separate decoding problems. So we get our X and our Z syndrome, and then we use the respective HZ and HX CSS matrices to decode these as two independent classical decoding problems. And what we get out from this is some sort of binary vector that we then map to a recovery operation, which is then applied to the quantum state. Okay. So given this process, how do we actually determine whether our decoding has been successful? Well, in simulation, what we can do is we can calculate what we call the residual error. So our CSS decoder will return two Pauli operations, and Pauli operation to correct X errors and one to correct Z errors. And the residual error is just the combined effect of these recovery operations and the actual error. That if we're doing a simulation, we know exactly what that is. Okay, and we say that decoding is successful if the action of this residual error is to map onto the +1 eigenspace of the logical state. Okay, so this is the same as saying that the residual error is equivalent to a stabilizer. And conversely, decoding fails if the residual error is equivalent to a logical operator such that this logical state, the information encoded in it, is changed. So our error correction protocol has failed. Okay, so what decoders can we use to do the decoding for these two separate error detection components? So one question you might have is, can we use the surface code decoders that have been around for a while and have been highly optimized and are now getting to the point where they might actually be fast enough to run on a real quantum computer decoding syndromes in real time? And the answer is, unfortunately, no. And the reason for this is that both union find and minimum weight perfect matching are matching algorithms, and these require a very specific structure from your quantum error correction code. And the specific requirement they have is that your quantum error correction code produces pair-like syndromes. So we can see that this is the case, for example, in the surface code. So here we have a bit flip error that lights up two syndromes. And as we increase the length of this error chain, the syndrome weight remains the same. So we see that the syndrome is still weight 2, and if we increase it by 1, it's still weight 2. So decoding is just a process of joining these pairs of syndromes. Okay, unfortunately, quantum LDPC codes in general don't have this matching property. So we can see this very easily by looking at the Hamming code that we saw before. If we just put an error on the first qubit there, we see that 3 syndromes are activated. So we can't use a matching-based decoder for this. What this means is that we need to use a much more general decoding algorithm, and I'll be focusing in this tutorial on the classical belief propagation decoder. Okay, so why belief propagation? Well, it's a very general algorithm that can be applied to any sparse graph. So we don't need the matching structure. And the other reason is that it's extremely fast. So belief propagation runs in linear time, it runs sequentially. And if you have access to a parallel architecture, it can, in principle, be almost constant in its complexity. Okay, so to provide some intuition for how this algorithm works, let's focus on the classical decoding case. Here we have a classical syndrome equation. And given this syndrome, the goal of decoding is to find some minimum weight estimate of the error given this measured syndrome. Okay, and assuming that we have a uniformly distributed error model, as might be, for example, the case in the binary symmetric channel, then we can express this as a marginalization problem, where we marginalize over a multivariate probability distribution that relates the probability of each bit being an error to the syndrome that's been measured. Okay, so we wouldn't want to do this exhaustively because that would scale exponentially in its complexity. So the basic idea behind belief propagation is that we can leverage some of the structure in the probability distribution given to us by the tanograph to compute these marginals more efficiently. Okay, so in practice, this is done using a message passing algorithm where information is exchanged between the bit and the variable nodes of the tanograph. So a type of belief propagation called the product sum algorithm actually computes the marginals exactly. If the graph is tree-like, in practice, quantum error correction codes usually aren't tree-like. However, what we find is that even if the graph has cycles, in the classical case, at least, it usually works reasonably well. Okay, so this animation here is designed to give you some sort of intuition as to how the belief propagation decoder works. So this here is the tanograph for a repetition code, and we have this error pattern here, shown by the bits with X's on them, and that activates the syndrome that we see at the top. Okay, so yes, in the first step of belief propagation, we assume that each bit in the tanograph has the same probability of being an error. So what this essentially means is that we set the probability of error to being the initial error channel. Okay, and then we run belief propagation, and information is exchanged between the nodes, and this probability distribution redistributes itself. And eventually, once we start seeing that the probability distribution isn't really changing very much, we terminate the iterations. And at that point, we can then make a hard decision on the basis of the output probability distribution by thresholding the probability such that all bits that have a probability above a certain value are set to 1. And then that gives us a hard decision, which is the recovery operation, which can then be applied to remove the syndrome. Okay, so the reason I chose this particular error configuration is that we can see something interesting happening when we start the iteration. Okay, so we see that in the first iteration, what happens is that we immediately, the probability distribution immediately shifts to this bit here. And the reason for this is that in the first step, oh, can you actually see the mouse? No. Yes, I can see. Yeah, in the first step, what happens is that this bit sends a message to this variable node, and this variable node says, okay, this variable node sends a message to this check node. This check node says, okay, I'm not satisfied, so it sends a message back. And then that information reinforces the belief that this bit is an error. Okay, right. However, when we then run the algorithm further, what we find is that we get more information from other variable nodes and checks in the graph. And then eventually the information propagates from this syndrome through to this syndrome. But this one is also unsatisfied. And if we go to the step just before the final one, what we see is that we have, yes, all four. Oh. Yeah, now we see that all 4 of these bits have high probability of being in error. But what then happens is a message is sent to here, and it says, okay, look, these three are all have high probability, and if we just have these 3 bits being in error, then these 2 syndromes are removed. But that isn't compatible with this bit also being in error. So in the final step, that information is propagated to the final bit, and then its probability goes to 0. Okay. So this is great. This algorithm can be applied to any graph. So we can apply it in principle to a surface code decoding problem. So this is the HX component of a distance-fied surface code. We can do the same thing again. Can initialize belief propagation and then run it. And we see that for this particular error configuration, it just works. So we can make a hard decision, and then we see the combined effect of the initial error plus the recovery operation just gives us a stabilizer, and the syndrome is removed. So from this, it appears that belief propagation actually works for the surface code. So let's look at what happens when we draw a threshold plot of a toric code decoded with belief propagation. For those of you who haven't seen these sorts of plots before, this is a quantum error correction threshold plot. On the x-axis, we have the qubit error rate, which is the physical error rate on each qubit. On the y-axis, we have the logical error rate. And what we typically do is we draw lines on this plot for a number of different error correction codes of different size. And once we start looking at this particular decoding plot, we see that this error correction protocol, i.e. the toric code decoded with belief propagation, doesn't actually work that well. And the reason for this is we see that as we increase the size of the code, so this blue line is a 162 qubit code, and the red line is a 450 qubit code. And what we see is that as we increase the size of our error correction code, the logical error rate is actually getting higher. So this is, in effect, an error worsening code rather than an error correction code. And this toric code decoded with the belief propagation decoder doesn't actually have a threshold. And the reason for this was touched on in the previous talk. It's because of the presence of these so-called trapping sets in quantum codes, and these arise when we have cycles that support degenerate errors. Okay, so the classic example is this configuration in the service code where we have a so-called corner error. So once we've run belief propagation on this, what we find is that the probability distribution eventually converges to showing that there's high probability of these 4 qubits around this square all being errored. So what then happens when we make a hard decision is that we apply a Z error on every single one of the qubits around this square, and it doesn't actually remove the activated syndromes. So these trapping sets cause the belief propagation decoder to fail, and this is why we don't get a threshold. Okay, so we have to find some way of dealing with these trapping sets, and perhaps the best way that we know of at the moment is the so-called order statistics post-processing technique. So the OST decoder is a technique for decoding parity check matrix. It always guarantees a solution that satisfies the syndrome. It's existed for a while, so it was initially developed as a method for lowering the error floor in classical LDPC codes, and it was first applied in the quantum setting by Pantelev and Kalashav in 2019. Okay, and the idea behind the belief propagation plus order statistics decoder is we first run belief propagation. If that belief propagation output satisfies the syndrome, then great, we simply output the BP solution. If not, then we call the OST decoder and output the OST decoding. Okay, and the basic idea behind OST is that we can always solve the decoding problem using matrix inversion. So consider this parity check matrix here. Of course, we can't immediately invert this matrix because it's not full rank square. But what we can always do is we can choose a full rank subset of the columns of this matrix and decode that instead. Okay, so the question now might be, why don't we just do this all the time? And the reason for this is that there are lots of different ways of choosing this subset of columns. So we could just pick 4 random linearly independent columns And it would give you a solution to the decoding problem, but it's not necessarily going to be a minimum weight solution. And in the context of quantum error correction, that would probably mean that you're introducing a logical error in most cases. Okay, so how do we get around this? Well, the idea is to use the probability distribution that's output by BP to intelligently select this subset of columns. Okay, so let's stick with this parity check matrix here. If we want to decode this syndrome, then we can put this into the belief propagation decoder, and it might output this sequence of probabilities, error probabilities on each bit. So this fourth bit in this case would be the one that's most likely to be an error according to belief propagation. We can then use that belief propagation probability distribution output to rank our qubits or columns of the parity check matrix from from most to least likely of being an error. Okay, and then the idea is that we rearrange the columns of this parity check matrix according to this ordering. So this is the original ordering, and now this is the ordering such that this column corresponds to the bit that's most likely to be an error. At this point, we can then perform Gauss elimination column-wise on this matrix to find a full-rank submatrix consisting of the bits that belief propagation has told us that are highly likely to be an error. Okay, and this improves decoding. So this is just the decoding plot we saw before, where we just had the belief propagation decoder. But we can turn on the OSD processing. And what we see is, first of all, we immediately get a much more considerable reduction in the error. So we get much more logical error suppression. So we see that this, at 1%, we're suppressing by about 5 orders of magnitude more. The second thing is that we also now have a working error correction protocol in that we actually have a threshold. So remember, the blue line is the smaller code and the red line is the biggest code. And as we increase the size of our toric codes, what we see is we get improved logical error suppression. So our error correction protocol is now working. So this is the way in which we can hack belief propagation to work for quantum codes. Okay, the big advantage of this belief propagation plus ordered statistics decoder is that it can work for pretty much anything. So all the examples I've given up to this point have been for the topological codes. However, it can be used to decode pretty much anything that is LDPC. So examples include fracton codes, 3D color codes, various topological codes, as well as circuit level noise decoding graphs. And now for some advertisements. If you want to try out this decoder, we have an open source software package that allows you to go from defining a parity check matrix in Python using NumPy to actually doing some decoding in less than 10 lines of code. Yep.
Maybe I missed something. Apologies if I did. I thought the reason you wanted to look at the belief propagation was that it's a local algorithm, but then this OSD where you have to sort the probabilities, that doesn't seem very local.
Sure, yeah, we'll get onto that later. Okay, so up to this point, I've described decoding in the very idealized setting of circuit level noise, of code capacity noise, sorry. Of course, this isn't very realistic because we actually have to use quantum circuits to measure our stabilizers. So in the code capacity noise case, what we assume is that the errors only occur in a very specific location. So this is an example of an error correction circuit for one of the simplest quantum codes, which is the 422 error detection code. Yep.
What is the time complexity of this, the BP plus OSD algorithm?
Okay, I have a slide on that later, so we'll get to it. So this is a 422 error detection code, and the HX and HZ matrices are just these. So the first part in our error correction circuits is create an encoder. We then get our logical state, and then we measure the X and the Z stabilizers, which in this case just Z, 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 and X, 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 out via projective measurements. Okay, so what this looks like in a little more detail is that we can use CNOTs to measure these. So this is the encoder now. This is the measurement of the Z stabilizers, and this is the measurement of the X stabilizers. And this is still a code capacity noise model because we're assuming that errors only occur at this location. But because, of course, this is completely unrealistic because these auxiliary qubits that are used to measure out the stabilizers are also qubits and are therefore just as susceptible to error as the qubits on the register. So what a more realistic picture of the circuit might look like just for bit flip errors is like this. So we have errors in every single location in the circuit, and we have to adapt our decoders to take account of this. And the reason this is problematic is because of error propagation through the circuit. And to understand this, we need to understand two rules for the propagation of Pauli errors through CNOT gates. So the way that this works is if we have an X error at this location, then a CNOT gate will propagate it like this. So we get an X error at the control and an X error at the target. And similarly for Z errors, what we find is that if we have a Z error down here, it will climb up the CNOT to give you an error pattern like this. So what this means is that single errors in our quantum error correction extraction circuit can spread to heavier weight errors and activate more syndromes than you might expect. Okay, so as an example, what we find if we have an X error hit in this part of the 422 syndrome extraction circuit is that it will propagate like this. So I'll activate both this syndrome measurement and this syndrome measurement. Okay, so given this more complicated circuit level noise model, is it sufficient to decode the quantum LDPC code using the techniques that we've been describing so far, i.e. just decoding the HX and HZ matrices as classical codes? And the answer to this is unfortunately no. So what we need is we need a much more detailed decoding graph that relates each sequence of measurements here to each specific error mechanism in our circuit. Okay, so what typically happens is that these circuit level noise decoding graphs get much bigger. However, one important thing to note is that they are still binary matrices, so they can be decoded using BPOSD. And the other thing to note is that these decoding graphs get much bigger. So in this paper, which will be the subject of the next talk, they decoded a 144.12 code under circuit level noise and had to use an 8,785 column decoding matrix. So we see that our decoding matrix increases from 144 to 8,785. So that's a pretty huge expansion in the complexity of the decoding problem. Okay, so this leads on nicely to the next section, which is the question as to whether BPOSD is enough. And now to answer your question about the runtime of this algorithm. So to recap, the belief propagation component is extremely fast. So it runs in linear time in the block length and almost constant when run in parallel. However, the big bottleneck in our belief propagation plus ordered statistics decoder is the OSD component, because that requires Gauss elimination, which is by comparison really slow. So it's cubic in the block length in the worst case, and also very difficult to parallelize. So the OSD component is really the bottleneck, and that raises the question as to whether this particular decoder that works so well for simulations and for benchmarking quantum LDPC codes is the actual decoding technique that we'd want to use in a real quantum computer when we're decoding real syndromes. So the open problem is there an OSD alternative that improves performance with reduced complexity? Okay, so the dream would be to have a completely local decoder using a combination of belief propagation and something like the flip decoder that was described in the previous talk. So the advantage of this would be that it would be a completely local algorithm. So the flip decoder only needs to know about individual bits in its immediate environment. So it could be arbitrarily parallelized, and this would, in combination with BP, which can also be very easily parallelized, lead to very fast decoders. So this idea has been explored in various works. However, what we find is that there's usually a pretty serious performance penalty. So this is a plot from some work I'm currently doing with Tom Scrooby from Okinawa University, where we're comparing the performance of BPOSD with the BP plus flip decoder. So the red line is BPOSD and the green line is the BP flip decoder, and you see that we're reducing performance by about 2 orders of magnitude. Okay. However, the interesting thing is that for this particular code, which is a very small quantum LDPC code, we're still getting improved performance compared to a comparably sized surface code decoded with matching. So I guess the question to be more further explored is, yeah, what is the compromise that or what is the performance hit that we're willing to settle on? Is potentially a faster decoder worth it if it means a reduction in the quality of the decoding? Okay, the second approach that we could look at is repeat until success belief propagation. So here the idea is that we can run belief propagation multiple times. And after each run of BP, we modify something about our decoding problem. So one example is to modify the error channel, and other techniques modify the decoding graph itself. On the right here, I have an example from this paper, the stabilization and activation decoding technique. And here, the idea is that you, after every round of BP, delete some problematic check nodes that are involved in trapping sets. And for a particular code family, they actually showed that you can improve upon the performance of belief propagation plus all the statistics decoding. What isn't explored, however, is the performance of this code in a wider variety of settings or under circuit level noise. Another approach is to abandon the idea of decoding your bit flip and phase flip errors separately, because this comes with a performance penalty. So some decoders have been proposed where you instead decode over a quaternary graph rather than a binary graph. So in some settings, this can give us performance that is comparable to BPOSD. What I find, however, is that these decoders are very difficult to calibrate, and they're often very dependent upon the initial conditions. And the final...
is it computationally expensive? Why is it more computationally expensive?
Because the belief propagation update rules get more complicated.
Okay. Can you quantify like how much was it?
I don't know the exact number, but yeah, it's more, it's slower. So the final thing I would mention are this idea to use machine learning to actually improve the belief propagation algorithm itself. So as mentioned previously, belief propagation works by exchanging information between check nodes and variable nodes. So the idea here is to use some sort of machine learning technique to learn better update rules. So here's one paper where they trained a belief propagation decoder using a graph neural network, and they do get performance that is approaching the BPOSD line. The problem, of course, with this is that, as with many things to do with neural networks, scalability can be a problem. Can you ensure that it still works once you start increasing the size of the codes? Okay, and that's the end of my talk. So to summarize, quantum LDPC codes require general decoders that go beyond union find and minimum weight perfect matching. BPOSD works reasonably well and gives us nice decoding plots for papers in our early simulations of these quantum LDPC code protocols. However, because of the cubic complexity of the post-processing, it's unlikely they will actually be practical when we're building real quantum computers based on LDPC code architectures. So the open problem is, can we improve upon OSD?
I was curious if the BPOSD algorithm is relatively easy to include information about the noise model. So if you have bias noise, where do you put that in?
Yes, it's very easy to include. So when you start belief propagation, you set all the bits to be equal to the initial error channel. If that initial error channel is biased, you just set the initial probability distribution to bias. So yeah, it works out of the box, basically.
So I'm kind of curious. I think Calderbank has a paper on spatially coupled codes where he just runs belief propagation. And I think the Tanner graphs have like girth 8, I want to say, and it seems to perform pretty well. What do you think the prospects are for getting rid of any post-processing completely in both the ideal setting where you're not worrying about circuit level noise, and then in the setting of like circuit level noise where you actually have to worry about quite a bit more?
Yeah, I think this is a good strategy. So yeah, if you can design your code such that it works well in the first instance, then that's the best way of going about it. So yeah, I guess this is the motivation behind many of these bias noise papers. As you get more bias, it becomes more classical, therefore easier to decode. So yeah, that is the best strategy if we don't find a technique for actually doing this processing.
If I may comment, so when you add the circuit level noise, then the girth of the graph, no matter what the original graph was, it becomes 3. So the generators for the circuit level noise always have, all of them have weight 3 or 2. The 2 you can eliminate, but the 3 remain, and that makes it very difficult. Basically, out of the box belief propagation always fails. BP plus OSD requires a lot of extra, sort of, because the original BP fails very often.
That's a question for Beck.
Yeah. So, what is the argument that BP converges in a linear time? You said like BP is a ON.
Yep.
How can we guarantee that iteration converges after ON time?
Okay, there are proofs of this. Yeah, I can't reproduce them on the fly. But
Another question is BP plus OSD better than the minimally perfect matching in the toric code phase?
no. So yeah, I guess this is the price to pay for the fact it's a very general decoder. So yeah, for the specific case of the surface code having a decoder that's optimized specifically for that decoding problem, performs better. You can improve the performance of the matching decoder by combining it with belief propagation. So yeah, Oscar, who is also here, proposed a combined belief propagation plus way clever matching decoder that performs improves the performance even more.
Can I stop? I have a question about criterion decoder. So this decoding problem is an estimation recovery operation from syndrome. And if I understand correctly, you described the protocol to construct the estimator in this talk. But there must be some criteria on the decoder. For example, random guess may also provide some estimator, but we don't call it as a decoder. There must be some criteria to call some procedure as a decoder. Do you have some criteria in your mind, or how BP plus OSD satisfies such a criteria? Do you have thoughts on this?
Sorry, I don't really understand the question. So criteria for
estimating recovery operation is a decoder, but this estimation needs to satisfy some condition in order for this estimator to call, in order to call some protocol.
Okay, yeah.
What's the criteria? What's the condition?
So I guess, yes. So in this particular setting, we're just assuming that the decoding matrices are classical matrices, and we're just trying to find the lowest weight solution satisfy this syndrome in the hope that this will not introduce a logical error. More accurate decoders can look at the actual cosets and try and differentiate between the logical classes that separate the different parts of the code space. So some of the tensor network decoders for the service code do that, for example, and are much more accurate, but also much slower. Is that the...
Yeah, okay.
Okay, perhaps we can...
So maybe this is a basis of your coding, your procedure. Am I correct?
Yeah, I guess the approach here is to make a decoder and then see where it works in terms of the decoding graphs, and then, yeah, if it does. But yeah, it's very difficult to actually prove things about belief propagation.
Yeah.
That's all.
Thank you for the question.
There's this, you mentioned union find can't be applied to general LDPC codes, but there's like this generalization, right, for more general codes. So is there a combination of belief propagation with this general union find, just like belief propagation with matching?
Yes, so belief propagation plus matching decoders have been proposed. The generalization of the union find algorithm that Nico proposed does have the problem that it's quite slow. because you have to do repeated Gauss elimination on all of the clusters as it grows.
Yeah.
The algorithms like belief propagation, do they also have, or can they be naturally implemented on channels like amplitude damping?
Potentially, that's not something I've explored though.
So in the measurement circuit you show, you always separate X measurement part and Z measurement part, and you can and I can imagine that this this kind of arrangement could be good at correcting one one type of errors, but might be bad on correcting the other type of errors. So is there any reason of you not mixing the measurement circuit of the two types of errors?
For simplicity, that was the reason for this particular example. But yes, scheduling is important, and the actual order in which you measure these syndromes can also affect the distance of the decoder graph. So yeah, in the next talk, we may see some discussion of that, because they explore lots of different ways of extracting the stabilizers and stabilizers.
Some of these machine learning decoders, how easy is it to say train on one code and transfer it to a different code? Are they all trained for like the specific code that they're trying to decode, or are they?
So yeah, my understanding is that for each instance of an LDPC code, you'd have to train a specific model. Yeah, this is another problem with quantum LDPC codes, because they're so random. It's not like a surface code where once you've figured out how to decode this full patch, you can essentially do it everywhere.
Any more questions? Oh, yes.
So you said matching-based algorithms might not work in general cases, but as far as I understand, this matching comes from the fact that the surface code is based on the homology, and the homology is present in every quantum code in general. So does it make sense to find minimum weight cycle or path in general quantum codes?
There are some ways of hacking more general homological codes to work with matching. It's not something I'm too familiar with. Our Amanda Quintavalle, who's sitting to your right, is working on that exact problem. So it'd be best to discuss with her.
But I think that the problem is how the symbol graph relates to the minimum weight solution of the decoding problem. So on the toric code, you always have like each qubit error leads up to syndromes. So you can map the problem of finding a minimum weight recovery operator to the one of finding a minimum weight path between the two syndromes. But for general codes that leads up more than two syndromes, you don't have the same mapping. So it's not.
Okay.
I think it's not down to the homology guess, but the number of. But there are a lot of matching people in this group.
Yeah.
I guess, one quick question to poke at the open problem a little bit. I think perfectly decoding to minimum weight a general CSS code is known to be NP hard, right? So the question is, like, where do we find hope to look for widely applicable decoders? You know what I mean? Like, where might we think to look?
Well, my hope is that some technique from the classical literature that's as of yet been untested in the quantum setting will work well. So OSD, for example, was such a technique. But yeah, I don't know specifically how it's going to be solved.
Okay. Any more questions? If not, let's thank Joschka again. We take a break.